In earlier videos in this series, we first looked at some of the problematic issues in Newtonian gravitation, and then set about trying to follow the thinking of Einstein towards his general theory of relativity. We started by exploring various aspects of Riemannian geometry and the metric tensor, focusing first on flat two-dimensional spaces and then moving on to explore some curved spaces. We looked at a variety of types of coordinates or metrics that might be used to make measurements in those spaces, and also how we might make transformations from one frame of reference to another. An important mathematical tool was introduced in the last video, number 7, namely the covariant derivative of a vector component and the associated Christoffel symbols. And all of this mathematics was with a view to getting enough of it under our belt so that we can press on towards an understanding, even a derivation of sorts, of the Einstein field equations. In moving further towards that goal, we want now to introduce the idea of the geodesic. The geodesic is often defined to be the shortest path between 2 points in a particular space. And although, as we clarify later, this description ought really to have some modification, we'll continue with it as a useful working definition for the moment. For example, in a two-dimensional flat space, we would consider a straight line between 2 points in the space to be the shortest distance between those 2 points, and we would call it a geodesic. In what situations wouldn't a straight line be the shortest distance between 2 points, you might ask? Well, let's see. Let's start with such a flat two-dimensional space. Once again, the space extends in all directions, but we show it here bounded by black lines for convenience. This time we'll also shade it in grey. The reason being it will be easier to display some sort of curvature when we move over to curved spaces. But for the moment, it's simply a flat Euclidean space, and as such, we could add Cartesian coordinates in the usual way, and we will assume here that the grid spacing is of unit size. The metric tensor for this frame of reference would, of course, be the identity matrix 1, 0, 0, 1. And furthermore, we can say that the metric tensor would be the same everywhere. If we could see this space embedded in a third dimension, it would clearly be perceived as being flat. No bulges or stretches or warping into any supposed third dimension. The space is not curved, and the Cartesian coordinates of x1 and x2 measure the space effectively in the simplest of ways, with a metric tensor that looks like this, 1, 0, 0, 1. And if we imagine lowering or projecting a set of nice, equally spaced, unstretched Cartesian coordinates down onto this surface, it would fit perfectly. And we could choose an origin for our x1 and x2 axes and make all the measurements we want. However, consider the situation now where a part of this space happened to be curved. We might not appreciate this when looking at this space directly like this, but we'll suppose that in very simplistic terms, it's curving out towards us in some way. However, if we had the benefit of appreciating the embedded dimension, then as outsiders observing from this angle, we will be able to appreciate any curvature. It's still a two-dimensional surface, but part of it has been stretched or warped into what seems to us to be a third dimension. It is curved in this region and flat in most other places. The metric tensor for this whole space will have to be some complicated function of the coordinates x1 and x2, and that function would have to be such that the metric tensor changed from being very simple around here to being very complex in this region. In order to cover both these aspects of the space, then in a very general way we could write the whole metric tensor like this, where each of the 4 components is a function of x1 and x2. For some parts of the space which are flat, this could of course be equal to the identity matrix 1, 0, 0, 1, but not near the stretched area. In this region, it would have to be this complicated function of x1 and x2. In other words, we could measure the space using simple Cartesian coordinates in some parts of the space, but certainly not anywhere near the bulge. Each point on the curved section, the bulge, would probably have different values of G11, G12, G21 and G22. And remember, as we discussed in video number 6, these four numbers would be to do with the angle between the x1 and x2 lines at the point and the extent to which the basis vectors would have had to be stretched or compressed to fit smoothly onto the bulge. Let's now consider the idea of a geodesic and use the simple idea of it being the shortest path between 2 points. We'll start with the simple situation of a flat two-dimensional space, one with no curvature at all, and we'll ask the question, what is the shortest distance between these 2 points, A and B? The answer, of course, would be the straight line path between the 2 points, shown here in green. This can be proved using Euclidean geometry, but it's fairly obvious to most people without the need for a mathematical proof. But what about when the space is curved in the way that we've just been considering? What seemed before to be the shortest path between A and B, going in what seemed to us to be a straight line from one to the other, is now not the shortest distance. The curving of the space has made that path much longer because the space has been stretched. To our eyes, with the insight that we have of the embedded dimension, it seems as though there is a hill to move up and down, and that makes the distance much longer. But of course there is no hill. There's no up or down in any third dimension, but there is extra measured distance in that seemingly straight path from A to B. That path over the stretched area from A to B is longer, say, than this path from C to D, even though the x1 coordinate difference seems to be the same for each. So what is the geodesic between A and B according to our simple definition? What is the shortest path? Well, it's probably something like this. It's certainly not a straight line. It's a curve. That said, however, it is straight in the sense that if you were on the surface and if you started from A and you pointed yourself in this direction, the direction of the red arrow, and you started moving, and if you kept moving in exactly the same direction, dead straight ahead, you would naturally follow this green curved path and end up at B. Looking at the two-dimensional surface from above, as it were, such that our perspective of the apparent bulge is not now visible to us, this shortest path from A to B, this geodesic, looks even more curved. We could perhaps illustrate the stretching of the space between A and B, the bulge, with something like contour lines shown here in light brown, which mimic a hill on a geographical map. Now, it's not normal to do this in teaching general relativity, but it might help here to visualize the curvature in this head-on view of the surface. The path shown in green is the shortest distance between the 2 points A and B, and is a kind of local minimum. What I mean is, any further this way for the path, and you're going to be out too far, making the path longer. Any further this way, and the path length will also increase because of the curved or stretched space, what you might call going up the hill. The green line here is the shortest path compared to other possible paths in that nearby region. It is a local minimum. This green line is not the only geodesic, of course. Assuming this curvature has a symmetric shape, there is another local minimum around this way. Okay, but what about the x1 and x2 lines over the stretch region? We've deliberately left them off the picture so far for the bump in the middle. Well, we could draw any lines that link up with those from the flat parts of the space, as long as we define what they mean, as long as we know the metric tensor for the coordinates that we draw. We could even try to draw straight lines of the Cartesian type, but they wouldn't end up as Cartesian coordinates. Imagine, for example, trying to lower or project a set of Cartesian coordinates down onto this surface. The contours near the bump would have to be stretched, along with their basis vectors to get them to rest on the surface, and that could be done in lots of ways. You could even force them to be stretched, something like this, in such a way that if you imagine looking at the coordinates without perspective, they might deceivably appear straight, like this. But of course they're not really straight, as we could see from a perspective view. Thinking about distances here, although these squares or rectangles, which are part of the flat regions of the space, look like Cartesian coordinates and may well be exactly that in that region, with unit-sized sides, there is no way they represent the same as these supposed squares or rectangles. This distance may well be 1 unit, but it's certainly not the same as this distance. But how can that distinction be true? Well, if you recall, it's all to do with the metric tensor. The coordinate lines may well look the same from this viewpoint, looking from above, as it were, but the metric tensor will be very different in different places. The units in these regions can always be chosen so that the metric tensor in them is 1, 0, 0, 1, because these regions are genuinely flat. And it can be arranged that the basis vectors E1 and E2, the measuring sticks if you like, would have a size of 1 unit, and the angle between them would be 90 degrees. We could even say that this distance is 1 unit. However, here, the metric tensor in this region would have to be some complicated function of position x1 and x2, and almost certainly different at every point in the region. Not only will the angle between the basis vectors probably not be 90 degrees in this distorted space, the basis vectors here will not be unity, and those facts will make distance measurements take different values. On top of that, as mentioned, the basis vectors and the angle between them will probably change continuously as you move from one point to another within this region. In other words, they will be different for different values of x1 and x2 on the bump. If we wanted to know, for example, what this distance here was, marked by this double-headed arrow, we couldn't simply say that because it is the distance between the two lines of the grid, it must be unity. It's not. We'd have to go back to basics, and on account of the fact that everything is changing here, we would have to measure the distance we wanted by adding up infinitesimally small distances, each of which is probably stretched in different ways, and then we would get the total distance represented by this line. Remember that the square of an infinitesimally small displacement ds is given by this expression, which for 2 dimensions such as we have here, when all 4 entries in the metric tensor are non-zero, turns out to be this. This is the microscopic distance squared between 2 infinitesimally close points, and in order to know the macroscopic distance between 2 points in the space, we would need to integrate all the little ds's over the path in question, and you would get a very different answer for the total distance than you would get, say, for this path. To put it crudely, the slope of the hill or the curvature of the space affects the metric tensor in such a way that measurements of things are radically altered. So, these are not Cartesian coordinates, even though superficially, from this particular viewpoint, looking from above, they might look a bit like them. They are curvilinear, at least in the bump section they are. However, you shouldn't forget also that we could actually have used curvilinear coordinates to measure the whole of the space, something like this. As long as we defined what the coordinates represented, in other words, as long as we knew the metric tensor for the whole of the space, this set of coordinates, in the other head-on view, would of course probably look something like this. In this case, with curvilinear coordinates like these throughout the whole of the space, the metric tensor in any and every region would not be the identity matrix, but rather a complex function of x1 and x2. Granted, knowing that certain parts of the space are actually flat, for example here and here, then we could transform the x1 and x2 values in those regions into something else, say x1 tilde and x2 tilde, such that the metric tensor for those regions was the identity matrix. but that wouldn't apply here. Try as we may, we would not be able to find an x1 tilde and x2 tilde conversion for this region, which would make the metric tensor equal to the identity matrix. And that's because this part of the space is definitely curved and must therefore be measured using curvilinear coordinates. However, whatever coordinates we do use to make measurements on this space, any calculation of a geodesic, which we're calling the shortest distance between 2 points across a region, will always give the same answer, the same route, and it won't necessarily be a straight line. Okay, one final point before we look at geodesics in some actual curved two-dimensional spaces. Although there's no way we can talk in terms of this region of our bulging two-dimensional space as being flat, we can talk in terms of an infinitesimally small flat space being at every point of the region, and we will call such things the tangent space. For example, if we zoom into a point on this bulge, any point would do, although we'll pick one where there are already lines to be seen, here at the red dot. At this point, the lines are curving. But if we get so close that we're looking at distances which are infinitesimally small, then the lines could be considered to be straight, something like this. Strictly speaking, these straight lines are the tangents to the coordinate lines at that point. And if, to help visualization, we extend those tangent lines as shown here, we can imagine them being part of a flat space with this kind of grid. And within this flat tangent space, the coordinates would be the same throughout, with the same angle between them and the same basis vectors everywhere within that tangent space. Again, we've limited the extent of this flat tangent space by boxing it in, although strictly speaking, it only really exists at the point, at the red dot, and we've only extended it so that we can appreciate it. You can probably best imagine this extended version of the tangent space as a sheet of flat card resting on the bulge and touching it only at one point, the point in question where the tangent space exists. Also, you probably realise that in this particular situation, we have basis vectors of this flat tangent space which are angled obliquely. But that's not a problem. We showed early on that angled, straight coordinates like this in a flat space with the same basis vectors throughout, stretched or otherwise, could easily be transformed into Cartesian coordinates with a neat square coordinate system, and the metric tensor could be made to be the identity matrix 1, 0, 0, 1 if we wished. This tangent space in these two dimensions is a flat plane, even if the extent of it, strictly speaking, is infinitesimally small, just at the point. I'm sure you also realise, if you think carefully about it, that if we were considering a three-dimensional space, then the tangent space at a point within it would be what we might call a flat volume rather than a flat plane at that point in the space, although we'll still call it a tangent space. In other words, regardless of the fact that the space may have curvature generally, at any particular point in the three-dimensional space, it can be said to be flat. So it could have, or be made to have by a coordinate transformation, simple three-dimensional Cartesian coordinates, such that the metric tensor for it could be written as the three-dimensional identity matrix in that infinitesimally small region, or if you like, at that point. Okay, so now let's look at an actual curved space, one that we know a little bit about, the surface of a sphere. And we'll think about the geodesics within that kind of space. The two-dimensional space that we've just looked at, although quite complicated in that it changes from genuinely flat areas to the complicated curved middle section, was at least simple to visualize. We could picture the whole space either with the benefit of the perspective of the third dimension and see the bump, or by imagining viewing it directly from above the surface, as it were, without the benefit of the perspective. In this way, we could also picture it with what might be said to be straight coordinates, or with curvilinear coordinates. We could also easily appreciate that, regardless of the coordinates used, the geodesic between 2 points on the curved part of the surface could not possibly be a straight line, at least as we tend to think of straight lines. However, perhaps the best illustration of the reality of geodesics is the two-dimensional surface of a sphere. The surface of any sphere is two-dimensional, and it's not a question of part of the space being flat and part of it being curved. It's all curved with the same curvature. And on top of that, you can't imagine in your mind's eye looking at the whole of the surface at once. You can't imagine having a plan view of it from above, as it were. This two-dimensional space is completely curved. Now, you might recall from video number 6 that the metric tensor for this spherically curved surface, the two-dimensional surface of a sphere, is given by r squared 0, 0 r squared sine squared theta throughout the surface, where r is the radius of the sphere, a constant for this surface space, and theta is the polar angle or inclination measured down from what you might call the North Pole. Now, although the angle phi is very much involved in determining position on the sphere, it's not included in the metric tensor. Changing phi does not change the metric tensor, whereas changing theta does. If we now imagine 2 points A and B on this surface, then it's fairly obvious that the shortest path between them cannot be a straight line, because seeing what we can see of the perspective, our third dimension viewpoint, we would say that a genuinely straight line would mean travelling through the inside of the sphere, and that's simply ridiculous if the space is only the surface of the sphere. It turns out that the shortest path between 2 points on the surface of a sphere must lie on what is called a great circle. A great circle is one which has the same radius as the sphere itself, and also has its centre at the centre of the sphere. Here's an attempt to show the great circle, which includes the points A and B. The centre of this black circle is at the centre of the sphere itself. The shortest distance, therefore, between A and B is then the path shown here in green. It's a curve on the surface of the sphere. Once again, however, if you started from A and moved in the direction of the red arrow, and if you continued in that direction, seeming to move in a dead straight line on the surface, you would eventually reach point B, having travelled the shortest path to get there. You would seem to have travelled in a straight line on the surface, but because of the curvature of the space, the path could be said to, strictly speaking, to be a curve. The fact that a great circle gives the path for the minimum distance from A to B can be proved using geometry and calculus. It's not a difficult proof, but fairly lengthy and fiddly, and certainly not worth spending half an hour on here. I think most people accept it without needing the proof. So this green line, the geodesic, is clearly a curve, and it is the shortest path from A to B. However, it's also worth noting that this green line around the other way is also what we would have to call a geodesic. Granted, this path is clearly very long, but it still has what we might call a local minimum length, in that it is a straight path as far as moving along the surface is concerned, and any slight deviations from it would make the path even longer than it is. It is a local minimum. However, we will continue to use the simple definition of a geodesic as being the shortest possible path between 2 points on a curved surface or in a curved space. Now, a lot more could be said about geodesics, but that's all we are likely to need, at least for the moment. An important concept, however, in general relativity will be the idea of the tangent vector in a multidimensional space or in space-time. It's obviously to do with the tangent space that we've just talked about, but let's think about it in some mathematical detail. In order to approach this idea and to get an expression for the components of a tangent vector at a point, It's usual to think at first simply in terms of a two-dimensional space. Consider once again, therefore, this two-dimensional curved surface, and again focus on the point indicated with the red dot. You'll notice once more that for convenience we've chosen the point to be at the intersection of two of the curvilinear coordinate lines of x1, which goes positive to the right, and x2, which is positive upwards and inwards. We said earlier that we can think in terms of there being a tangent space at such a point, and we can picture this tangent space as a flat sheet just touching the surface at the point and parallel to the surface at that point. Obviously, the tangent space only really exists at the point on the surface, but drawing this sheet outside of the surface helps us to appreciate it. You should be able to see that the coordinates we've used on this small orange sheet, the blue axes, are parallel to the tangents of the x1 and x2 lines at the red dot, and so they are what we've been calling angled coordinates, which are parallel with the x1 and x2 coordinates at that point. We can also imagine two vectors to be pointing along these axis lines in the positive x1 and x2 directions, shown here with blue arrows. Clearly these are two special tangential vectors at this point, and would have the same directions as the basis vectors e1 and e2 at that point. If such vectors had unit size and no units, we would call them tangent vectors, not just tangential vectors. Clearly though, there are an infinite number of tangential vectors at the same point and in the tangent plane, and each of these vectors would point in some direction or other along the imaginary flat sheet. Remembering, of course, that such vectors are indeed at the point, even though we show them as extended arrows for illustration. We're thinking of things like velocities or field values or whatever at the point. However, even though there are a multitude of possible tangential vectors through a point in a curved space, there is often a particular vector through the point that is important in a given situation within general relativity. And that is the tangential vector in the direction of some trajectory which may be passing through that point. For example, imagine we had a trajectory which might or might not be a geodesic, such as this green line. It shows the path of an object on this two-dimensional curved surface which passes through the point in question. At that point, the green trajectory could be said to be going in a particular direction, shown by this extended green arrow, and of course it is in the tangential space of the point. Let's take away the rest of the trajectory and concentrate on the part of it at the red dot. Now let's assume that this vector which represents it is dimensionless and has a magnitude of 1. It would then be called the tangent vector of the trajectory at that point. And in two dimensions it would clearly have two contravariant components, and also of course two covariant components. Now it turns out, and we'll prove this in a moment, that a useful expression for the contravariant components of such a tangent vector is this expression, written in the Einstein notation form. Now don't worry if this seems a bit strange, it's actually quite simple. For a start, in two dimensions it would represent two such contravariant components for this green vector, one in each of the axis directions x1 and x2. You should be able to see that these tangent vector components are dimensionless, they have no units. It's distance divided by distance, and they will each probably be less than 1, but they will represent vectors which will add up to the tangent vector itself, which in this case here does indeed have a magnitude of 1. But we'll get to that in a moment. To get an idea as to how this expression for the contravariant components of the tangent vector come about, and to illustrate what's going on, we can home in on the point on the surface, the red dot, and consider infinitesimally small distances such that the coordinate lines of x1 and x2 become virtually straight, as does the green line of the trajectory passing through the point. We can now take away the blue arrows. These black lines are the x1 and x2 axes at the red dot. This whole diagram represents an extremely small region of the surface. But let's go in even closer. Let's consider an infinitesimally small part of this green trajectory, which we'll call the arc length, and to which we will give the size equal to ds. Remember once again that this ds is really at the point where the red dot is, even though we're drawing it here extended in order to appreciate it. The size of ds will eventually tend to 0. Also remember that this green trajectory has direction, so that we could consider ds here to be a vector, in which case I'll give it an arrowhead and write it as ds in bold. In terms of components, we can say that this vector ds could be made up of two vectors along the x1 and x2 axes, and we could draw their contravariant component values dx1 and dx2. Also, given that the tangent space is flat over this infinitesimally small region, this can be illustrated using a parallelogram. I should stress that in this diagram, ds is a vector, and the orange arrows here are its two vector components, but dx1 and dx2 as written here are simply the size of those component vectors. They are the contravariant component or measured sizes of the components. If we wanted to write something which represented orange vectors themselves, we'd have to include the basis vectors, something like this. But let's just consider the sizes of the components, the contravariant components themselves. Clearly, at this microscopic level, this tangent space is simply a flat space with what we've been calling angled axes. In fact, all tangent spaces can be considered to be flat, and in general they will be made up of angled axes which are not necessarily orthogonal. If we now divide all three of these things, the vector ds and the two contravariant components dx1 and dx2, by the magnitude or size of ds, then we would have this. However, this ds by ds must be the tangent vector to the trajectory. Why do I say that? Well, it is a vector divided by a scalar, so it's a vector, and it points along the trajectory. Also, it has unit size. It's a vector divided by its own size. In other words, it is a vector of unit size with no dimensions. It is a tangent vector, and it is the tangent vector of the trajectory at that point. And we'll write this tangent vector using this curly T. Now, make sure you're comfortable with this. The green vector T here is now the tangent vector at the point on the original green trajectory. It has a size of 1 and no units because it was the vector ds divided by its own magnitude. However, it does have direction, and it can be said to be made up of two components in this two-dimensional tangent space. As you can see from the diagram, the values of the contravariant components of this tangent vector are given by these equations. T1 is dx1 by ds and T2 is dx2 by ds. And these can be written, of course, in the Einstein summation convention as Tm equals dxm by ds, which is what we wanted to prove. Later, when we discuss four-dimensional space-time, the index m will run from 0 to 3, and we will have a tangent vector in four-dimensional space-time. Whatever that means. One thing we can say that it does mean, however, is that this formula will represent these four contravariant components for the tangent vector of a point or an event on a trajectory in that four-dimensional space-time. When we get to thinking about this kind of thing, we will have to think about what this rate of change of time with respect to ds could possibly mean. But that's for later. Now that we have this equation for the contravariant components of the tangent vector at a point along any trajectory in m-dimensional space, we can think about the equation of a geodesic. In other words, we can consider writing down an expression which will describe a geodesic path on, for starters, a two-dimensional surface, basically its equation. Once we've done that, of course, we can fairly easily extend the result to any kind of multi-dimensional space, and we will then have the equation of a geodesic in spaces with any number of dimensions. In what follows, I will probably overuse the words actual and measured. The actual being what's really going on, the underlying reality, and the measured being what readings we get from the metric about what's going on. So here goes. If you recall, we said earlier that in order for a trajectory to be a geodesic, it must travel along the actual straightest possible path from one point to another, even when the space that it's travelling through is curved and the system of measurement, the metric, is curvilinear. The geodesic is straight, and yet it may be measured to be curved. This requirement of straightness, of actual straightness, means that the tangent vector of the geodesic must not change as you move along the trajectory. The tangent vector must remain constant on a geodesic, because only then can an object travelling on that geodesic be said to be tracing out the most direct route from one point to another. Now, this short section on the equation of a geodesic may well seem quite heavy going mathematically, but try to stick with it. Try to get a feeling for the results and try to hold on to it. The general idea from it will be important in the foundation of Einstein's field equations later. In order to find the equation for the geodesic, we must create an expression for the likely changes in the tangent vector over the trajectory, and then we must put that expression equal to 0. In other words, we will force there to be no actual change in the tangent vector, and we'll then be left with what should be the equation of a geodesic, which will involve the measurements we get. We'll start with an expression for the ways in which a tangent vector changes, indeed the way in which any vector changes with distance or displacement, namely its derivative. However, we should now realize that in order to get a meaningful derivative, we must take the covariant derivative of the tangent vector, as that is the one which will take the curvature of the coordinate system into account. In the last video, number 7, we found that the expression for the covariant derivative of the contravariant components of a vector v was given by this expression, where this is the measured derivative using the coordinate system or metric, and this is the correction factor for that metric and is made up of Christoffel symbols containing the metric tensor and its derivatives. And this, of course, gives the actual way in which the vector changes, its covariant derivative. If we therefore substitute the tangent vector Tn for the Vn in this equation, it will give us an expression for the actual rate of change of the tangent vector with position in the xm direction, where we can make m what we like. In a sense, this expression can be called the invariant rate of change of the tangent vector, because it is independent of the coordinates used, as all of the curving of the coordinates is taken into account via this term with the Christoffel symbols in it. Now, look at this equation. There's nothing new here. This simply tells us about the covariant derivative of the tangent vector t at some point in space. This is the measured derivative of it, which will depend on the coordinate system, but this is the actual derivative because it has been adjusted for by the Christoffel terms to compensate for the curvature of the coordinate system by using the metric tensor. As a reminder, in 2 dimensions this formula actually stands for 4 equations, and each equation will have a straight derivative term and 2 Christoffel terms because of the sum of r in these 2 dimensions. We have to take the derivative of t1 and t2, each with respect to x1 and x2. However, rather than writing out all the equations, let's try and work within the Einstein summation convention and simply take this as the actual rate of change of the tangent vector components as xm changes, where we are not going to say what m is. If we now multiply this equation by a definite but small change in xm, which we'll call dxm, we'll find out how much the tangent vector itself will change over that small distance dxm. Notice that this dxm is not the partial delta xm, but represents an actual but infinitesimally small change in xm. I suppose some people would insist that we use something like the capital delta symbol for this and write it like this, or maybe even put an A inside it just to remind us that this is an actual but very small change in xm. But we'll leave it like this. We could call the result of this whole multiplication capital DTN because it will be a small and infinitesimal change in the tangent vector component Tn due to that small change dxm in xm, independent, of course, in this case, of the coordinate system. In other words, it's how it actually changes. Again, some might insist that we write it using the capital delta sign, something like this, to signify an actual but very small change in Tn. But again, we'll leave it like this. Now, if you're still a bit uncertain about interpreting the Einstein convention and therefore not sure exactly what this equation is saying, we can say that in two dimensions, if x1 changes by dx1 and x2 changes by dx2, then each of the two components of the tangent vector t1 and t2 will change by capital DT1 and capital DT2 given by these two equations. And as is typical of these type of equations, you'll notice the actual change in T1, which is the x1 component of the tangent vector, depends on the changes in both x1 and x2, and similarly for the change in the T2 component. Okay, so now that we have this equation giving the actual small change in the tangent vector for a small change in x, or rather changes in the contravariant components of the tangent vector for small changes in x, we can now replace this with our expression for the covariant derivative of the tangent vector, which is the ordinary derivative plus a compensation from the metric involving Christoffel symbols. Doing that substitution gives the following equation. If we now multiply out the bracket, we get this expression. At this point, it should be clear that this represents the actual change in the tangent vector for small changes in dxm. However, what is this? Well, if you think about it, this whole term must represent the measured change in the tangent vector with no compensation for the metric. And so we could write this whole term as little dtn, once again using d rather than a delta. So we have, for a small movement along the trajectory of dxm, that the actual change in the tangent vector is equal to the measured change in it plus a correction term depending on the metric or the Christoffel symbols at that point, and also on the value of dxm and on the tangent vector. That, I think, should be no real surprise. Again, as a quick reminder, if we're in two dimensions, then this is two equations, each of which has one dt term and four Christoffel terms. These two equations tell us the small actual change in each of the contravariant components of the tangent vector for changes in position, the x1 and x2 values, along the trajectory. We said earlier, however, that in order for a trajectory in a space or a curve on a surface to be a geodesic, then the tangent vector must not change as you go along the trajectory. In other words, any actual change in the tangent vector over the curve must be 0. And this must be true at all places along the curve. And so that means that in two dimensions, both of these equations must be 0. Or more generally, using the summation version, we can say that dtn must be 0. And that, of course, means that this expression must be 0 if this tangent vector is to be part of a geodesic. Rearranging this, we find that the condition for a trajectory to be a geodesic is that at each point along the trajectory, the tangent vector must obey this equation, which of course, in two dimensions, is two equations, each with four terms. Now this equation is kind of saying that for a path to be a geodesic, any measured change in a component of the tangent vector must be compensated for by an equal amount from the metric via the Christoffel terms, and so be equal to the negative of it. This equation could be said, therefore, to describe the motion of a geodesic. However, we can manipulate it just a little bit further. Let's divide both sides of this equation by ds, the infinitesimally small distance along the curve that takes place when xm changes by an amount dxm. This then will give us the equation for the measured derivative of the tangent vector with respect to distance along the curve of the geodesic, namely dtn by ds. Now again, just as a reminder, in 2 dimensions this would be these 2 equations. However, this part of it here is equal to the tangent vector with an m index, tm. And so we can write this whole thing as this. And finally, one other manipulation of this equation is useful. On account of the fact that the tangent vector tn is given by dxn by ds, it means that this dtn by ds is really a double differential of xn with respect to s, so that the geodesic requirement finally becomes d2xn by ds squared equals minus gamma n mr tr tm, which in 2 dimensions would be these 2 equations. And that's it. This is our final version of the equation of a geodesic. And if you're travelling along a geodesic, this relationship must be true. Any measured acceleration away from a straight line will essentially be due to the metric. Now granted, this equation is in summation convention shorthand, and if you're not too familiar with interpreting things like this, it can seem extremely awkward. But what it's actually saying, crudely, is that as you move along the geodesic, the double rate of change of each of the coordinate measurements with respect to the distance you're travelling, ds, must be equal to the negative of these Christoffel terms. Okay, that might not be much more helpful, so let's expand things out again, at least for 2-dimensional space. Here's what the geodesic equation is saying for 2-dimensional space. Here are the 2 equations. Look at the first of these equations. The left-hand side can be thought of as the measured acceleration, for want of a better word, of the x1 measurement with respect to the geodesic direction as you travel along the geodesic, ds. It tells you how the trajectory curves away from what would be measured to be a straight line. If this measured d2x1 by ds squared is not 0, it means that the trajectory is being measured to go in a curve. However, that's not a problem, providing this d2x1 by ds squared is equal to, or if you like, is produced by, all this lot from the metric tensor at that point. Because if that's the case, then you know that the actual trajectory is showing no departure from an underlying straight line within the space. There's no actual departure from the geodesic. There may well be measured departure from a straight line, but that will be on account of the metric. And so going back to an earlier equation for the actual change in the tangent vector for a geodesic, this is 0. Now it's quite important that you try as best you can to get at least a reasonable feel for this geodesic equation and for where it comes from. Even if you only sense that it is keeping the geodesic on the straight and narrow, whereas the actual measurements might look curved. The reason it's important is that when we come to think about the construction of Einstein's field equations, we will need to use it. So bank this idea in your brain as best you can. As has been mentioned, one of the key points about general relativity is that freely falling objects are considered to move along geodesics. They go in actual straight lines all the time, even if you measure them to be deflected or to go in curves. Forget about gravitational forces and the like. Any measured departure from straight line travel is because of space-time and the metric or the measuring system that is being used to measure that space-time. Of course, when we do get to consider general relativity and four-dimensional space-time, it will mean that this equation for a geodesic will be horrendously complicated. It will represent four equations, each of which will have 16 Christoffel terms. And in that general relativity situation, S may also be considered to be time, the proper time experienced by someone travelling along the geodesic curve. In that case, this term will be a kind of measured acceleration away from the seemingly straight line travel. Again, it's okay to have a measured value of this, for it to be measured to be curving, but only if that measurement is equal to the things on the right hand side can the motion be said to be on a geodesic, an actual straight line. We need now to think a little bit more about the transformation of vectors between different frames of reference, or rather, as we know that vectors themselves don't change just because you measure them differently, we are really discussing transforming the measurements of those vectors between one frame of reference to another. You should be becoming aware that we're going to need to know how to transform the various measured components of vectors, or more realistically, the measured components of tensors between one reference frame and another. We'll be thinking in more detail about higher rank tensors in the next video, but sticking with vectors for the moment, the question is therefore, how will the measurements of the various components of a vector, any vector, change as we transform to an entirely different frame of reference? If you recall, we discussed the simple one-dimensional case of this in video number 3. In that situation, having only one dimension meant that we had only one component of the vector, and that was its measurement, and so we could talk about the vector itself being either contravariant or covariant. As an illustration, we took the vector, either contravariant or covariant, to be at a point in the one-dimensional space, and we considered making measurements of it using two different scales or frames of reference. These reference frames were illustrated as a red linear scale x1 and a blue distorted scale x1 tilde, like this. The position of the vector in the space is shown to be at the black dot on each of the scales. From that discussion in video number 3, we found that if the vector in question was contravariant, then the measurement made in the red frame v-con could be converted to the measurement in the blue frame v tilde con, like this. The conversion factor turned out to be the rate of change of position in one frame by the other. In this case, what you are changing into, tilde, was indicated in the top line of the differential. We also found a similar situation for a covariant vector in this one-dimensional space, but this time the conversion factor differential was the opposite way up. For these covariant vectors, the frame that you're changing into determines what's on the bottom of the differential. Of course, the same thing would apply to transformations going the other way, where you would be converting the measurements from the blue tilde frame to those made in the red frame. The same rule would apply, namely that the frame that you are changing into determines what's on the top of the differential for contravariant and on the bottom for covariant. And we'll get rid of these to save clutter. I think that was all fairly straightforward, I hope, and you can go back to video number 3 to think about it all again if you wish. However, now that we're considering 2 or more dimensions, we don't necessarily have to consider whether or not the vectors themselves are contravariant or covariant, because any vector can have what we have been calling contravariant and covariant components, and you'll see the reason for that naming in a moment. Right now, however, we're going to need a way of converting, say, the contravariant components of a vector in one frame to those made in another, and separately, the covariant components in one frame to another. To see how to do this, we will first consider a vector v at some point in a two-dimensional space. Suppose the vector v is here in this space, at this black dot. Never mind whether the vector is contravariant or covariant. Let's now think about its various components, but of course any components would have to relate to a particular frame of reference. So let's start by using this red x1, x2 frame of reference, which is clearly curvilinear. We could make measurements with this reference frame and we would get 4 values for the components of the vector at the point, namely v1 and v2 upper, contravariant, and v1 and v2 lower, covariant. Alternatively, of course, we could make measurements using a different reference frame, say this blue x tilde system. And if we did this, we would of course get 4 different measurements for the component values, which we could call v1 tilde and v2 tilde upper or contravariant, and v1 tilde and v2 tilde lower or covariant. However, it should be obvious that these blue measurements must be related to the red measurements in some way, and it should also be obvious that the relationship must have something to do with the way the x's in one frame change with respect to those in the other. Let me give you the answer to those relationships straight away and then try to justify them afterwards. Here are the 2 conversion equations that we would find for this situation if we did all the mathematics. They are written in the Einstein summation form. I'm sure you'd agree that this looks somewhat similar to the equations we had for the one-dimensional case, and we were talking about contravariant and covariant vectors rather than components. The similarity is that the conversion factor is the differential, and for the contravariant components, the differential has the x for the frame that you're going into on the top, tilde here. You could say that the multiplication factor, the differential, is new over old for contravariant. On the other hand, for the covariant components, the differential has the x for the frame that you're going into on the bottom, old over new. And it is perhaps at this point that we can maybe see why these 2 types of components were given the names that they were, contravariant and covariant, when those words were originally chosen to describe 2 different types of vectors in one dimension. It's because these different types of components transform in a similar way to either contravariant one-dimensional vectors or covariant one-dimensional vectors. Again, before we look at any kind of hint at a proof, let me unpack one of these equations for a two-dimensional space. Take the first equation, the one for converting the contravariant components of V from the red to the blue tilde frame. In 2 dimensions, this represents 2 equations from the m here, and each of them will have 2 terms from the n. Here are those equations. You should note that the measurement of each of these blue V tildes depends on both measurements of the red V1 and V2, and this must be because of the way both the dimensions could be stretching and twisting in these reference frames. The other equation for covariant components would give us a similar pair of equations for V1 tilde and V2 tilde. This means that we have 4 equations altogether to describe component measurement changes from the red frame to the blue frame. But how did these transformation equations come about? I did say I would hint at the proof. Well, it obviously has its roots in the one-dimensional case, but with extra complications. Here is the vector v at the black dot, the green arrow representing its size, and it's being measured in the red two-dimensional frame of reference. These black lines are essentially the axes at that point. The black lines here are meant to represent the red axes of the basis vectors at the point where the black dot is. I've tried to draw them parallel to the coordinate lines passing through that point, so they are essentially the relevant axes in the tangent plane. Remember, the space itself could be curved, though that is not assumed. The 4 components then could be illustrated like this. 2 contravariant and 2 covariant. If I take away the other coordinate lines, it may look a little clearer. Remember, all of this is at the point, not extended in space, which such diagrams can seem to imply. You should be able to distinguish the covariant lower index components because I've added an indication of the perpendiculars being dropped. Now, in a similar way, this is the situation for the measurements in the blue frame. Again, the black lines here represent the directions of the basis vectors of this blue frame at the point where the vector is, at the black dot. Once again, these 2 black axes can be used to illustrate the 4 components in this blue frame of reference, like this. If I take away the other coordinate lines, you can see this more clearly. Next, let me combine these 2 diagrams together, the red and the blue, and we'll change the black lines to red or blue as appropriate and label them all accordingly. Okay, it's a bit messy, but we can now see all 8 components of the same vector, 4 measured in each frame, and we can see how they are related to one another geometrically. And this is where the mathematics comes in, which we're not actually going to do. But if we started such a calculation by asking the question, say, what is the contravariant measurement V1 tilde in terms of the other things measured in the red frame? You could chase the angles in this diagram using what you know to be the various angles between the 4 axes at the point, using multiple angle formula, the sine rule, and other mathematical tricks of the trade. And you would end up, after a fairly messy calculation, with the blue V1 tilde component measure in terms of the red V1 and V2 measures, all from geometry. And it would come out to be this. Similar calculations for the other 3 blue measurements in terms of the reds would give these, giving us 4 altogether. 2 for the contravariant upper components and 2 for the covariant or lower components. You would then hopefully see into this set of 4 equations the possibility of using the Einstein summation convention to give these 2 equations, one for contravariant components and one for the covariant. Anyway, it's very important that you take on board these 2 distinct ways in which the values of the measured components of a vector transform when using different frames of reference. In one sense, the formulae are simple. They each form the new component by multiplying all the old ones by partial differentials. But to get the new contravariant component, you have to have the new blue x on top in that differential, just like the index on top. Whereas to get the new covariant component, you have to have the new blue x on the bottom of the differential, again, just like the index itself on the bottom. Now, these relationships will crop up again and again with vectors and with tensors when we come to them. This will happen as we move from one frame of reference to another when thinking about gravity and acceleration, and so it's vitally important that you are reasonably comfortable with them, at least in the sense that you understand roughly what they mean and what they do. And that's it for this video, except as a final short exercise with this, it might be worth getting practice at expanding out the Einstein summation convention equations for 3 dimensions. Let's look, for example, at the general conversion equations for contravariant components, which is this, and work things out. In 3 dimensions, the superscript m here is 3, so there will be 3 equations, and each equation will have the same number here for x tilde. However, each equation will have 3 of these, as this is a repeated index running from 1 to 3. Working through all this gives the 3 contravariant component measures in this blue frame in terms of those in the red frame to be this. And you can probably imagine what 4 dimensions would look like. Anyway, we now need to move on to thinking about tensors, or rather tensors of higher rank than those which we've been looking at. We've thought a lot about what can be called tensors of rank 1, in other words, vectors. But in order to get to Einstein's field equations, we need now to think about tensors of higher rank, which we will begin to do at the start of the next video. This video number 8 discussed the geodesic, and in particular we worked through to the equation for a geodesic. In the next video number 9 we'll move on to thinking about tensors and their transformation from one frame of reference to another, and looking at the covariant derivative of tensors.